Hello all. So this is the beginning of the course Basics of Non-Parametric Test with an Application by R. So as I have already told in the introductory video that this is going to be a 2-credit course and we are going to cover this course by 10 hours. And today we are going to start the module 1. In module 1 we are going to learn why non-parametrics, and under this module this is the first lecture where we are trying to see the need of non-parametric inference. Okay, so let's begin the journey. So in this lecture we are going to cover few points: parametric inference, advantages of non-parametric inference, recap on parametric test of hypothesis, merit and demerit of non-parametric tests. So this is going to be a very rudimentary concept related to the non-parametric inference, and to be more specific, related to non-parametric test. So what is a parameter? In statistics, parameter means a characteristic of the population, and parameter is used to recognize a family of probability distribution. But this word can also be used in a broader sense to include almost all descriptions of population characteristic within the family of distribution. So what we need to remember, what we need to keep in our mind, that parameter, whenever I am referring parameter, that means I am referring to a population characteristics. For example, the property of central tendency. I hope all of you are aware of central tendency, measures of central tendency, measures of dispersion, so on and so forth. So the property of central tendency of a population is generally marked by population mean or population median. Therefore, population mean, mu, generally denoted by this Greek alphabet, or population median, well, let us stick to this mu median notation for the sake of mathematics. These are the parameters. Okay, so population parameters are the characteristic or the property of the population. Okay, so what is parametric statistical inference? A subset of statistical population is a sample. So a part of population is called a sample. Inductive statistics or statistical inference is a field where sample observations are used to throw some lights on the population characteristic aka parameter, say theta or say mu. Now when I'm saying that throwing some lights, what does it mean? Throwing some lights means we want to infer, we want to say few information related to the population parameter. Why? Because generally population is unknown and the part of the population, that means the sample, is known. So with the aid of sample, we want to say something about the population parameter. And that's the context of the inductive or inferential statistics. Mathematically speaking, suppose x1, x2, xn be the sample observations, then a statistic, already I have defined that statistic is nothing but a function of sample observation, and we denote that statistic by t of x1, x2, xn. Statistical inference strategy is designed in a way to study the parameter using its sample counterpart called estimate. Let's say we are interested in population mean, then we have to estimate, we have to infer about population mean by the sample mean. There are two types of problem under statistical inference. One is estimation, that means statistical estimation, and another is test of hypothesis. Classical inference or parametric inference, just mind this, that parametric inference is analogous of saying classical inference. Okay, so is based on few specific assumptions on the population. In fact, under these standard assumptions, the inferential techniques emerge as optimum. Now, one question might trigger in your mind that what does it mean by optimum? Optimum means it will give, or the inferential strategy will give better result. To be more specific, it will give the desirable results. Okay, so classical statistical inference, whose justification in probability is based on these assumptions about the population, is called parametric inference. One more point to be noted, that classical inference is based on some assumption on the population. Okay, mark this word populations. For example, many a times we refer a sample by saying, let x1, x2, xn be n observations from normal mu sigma square. So that's our beginning line. Now, when we are saying that, well, my random sample, let us assume my random sample observations x1, x2, xn are coming from normal mu sigma square, that means we are imposing one certain aspect of the population. And what is that aspect? That is, the observations are coming from normal. The population is a normal population. So this is one type of assumption. Most usually we use this assumption. However, in a real problem, or when you are dealing with real data, everything does not come with such levels of populations assumptions. Most restrictive assumption is made on that normality assumption. That means we are considering the observations which are coming from the population. That population is a symmetric population, mold shaped with a single peak. You can see the picture. You can see the picture here. So it is not at all a bimodal. It is not at all multimodal. It is symmetric. That means left part, if you draw one axis of symmetry, the left part will be similar as the right part. So what happens if the population looks like positively skewed? In the left picture, you can see that this population has a longer tail towards the right axis of x. And look at the second picture, this population has two modes, two peaks. And look at the third one, the tail of the population is towards the lower value of x-axis, that means towards the left tail. Okay, so for each of these three cases, one might notice that assumption on symmetry falls short. Now, this symmetric assumption, how come all of the time we are sticking to this symmetric assumption? There is one noted statistical result which is called central limit theory. Central limit theory states that the probability distribution of sample mean x bar in notation is Gaussian or is normal. Well, just a quick reminder that Gaussian is another name of the normal distribution for sufficiently large n. So mark this word, for sufficiently large n. So when your observations are quite large, then any distribution or the observations coming from any distribution can be converted to a very desirable Gaussian distribution or Gaussian setup. Well, there one point will trigger in your mind that what happens when your n is very small, when your sample size is pretty small, so that you cannot make the assumption of central limit theory. There comes the need of non-parametric inference. Okay, So there are 2 points to be noted. First point is when your population is non-Gaussian, number 1. When your sample size is extremely low, there is no scope of defining or assuming the Gaussian setup, then you have to take the aid of non-parametric inference. So is there any assumption to be assigned for applying non-parametric inference? Yes, there is one assumption, and that assumption is enough. What is that assumption? That assumption is the population is continuous. Just this. So what are the advantages of non-parametric inference? Non-parametric methods are generally quick and easy to apply. The merits of non-parametric methods stem on its extreme generalizability, that means on its unrestricted behavior. And the third one, in presence of, very important one, in presence of dirty observation. So what does it mean by dirty observation? That means in presence of extreme observations, statistically speaking, in presence of outliers, non-parametric inference performs well over parametric inference. Now remember that when you know that your observations are coming from normal distribution, then non-parametric inference will not give you better power. Okay, I'm coming to that point later on. Well, there is another point to be remembered, that in statistical literature, there is one more term which is sometimes synonymous, sometimes used as a synonymous term of non-parametric, that is called distribution free. But my dear student, there is a slight difference between non-parametric methods and distribution free method. As in distribution free procedure, the inferential method does not depend on the parameters or on the form of the distribution, even they are known. So distribution free method is the inferential strategy where you are not using any parametric help, any parametric information. Clear? Okay, so let us come straight down to non-parametric test. So what are the needs of non-parametric test? Let us have a quick recapitulation of testing of hypothesis. I mean the parametric testing of hypothesis, which you have done already earlier, I presume. The test constructed on population parameter. Okay, so basically test hypotheses are constructed on the population parameter. There are 2 types of hypotheses one may encounter with. One is null hypothesis, another is alternative hypothesis, and we know how to write null hypothesis and alternative hypothesis by H0, H0 or H1 or HA. H1 means for alternative hypothesis. So H1 is true if the null hypothesis is false. That means H0 and H1 are mutually exclusive. H1 is also called research hypothesis, usually of the form H0 theta is equal to theta 0 against H1 theta not equal to theta 0, theta greater than theta 0 or theta less than theta 0. I hope you understand theta here is the parameter. So when I am writing the alternative hypothesis as theta greater than theta 0, that means it is a right tail test. And when you are writing theta less than theta 0, that means it is a left tail test. And whenever we are using theta not equal to theta 0, that means it is a two-tailed test. So the rejection region or critical region and acceptance region based on the sample observation X. And what to reject? We have to reject the null hypothesis. So the result or the conclusion should be like this: we reject the null hypothesis. We never say that we reject the alternative hypothesis. We reject the null hypothesis or we fail to reject the null hypothesis. Now the sample space, what does it mean by sample space? That the space which contains all of the sample observations. Here I have used as X So X is equal to W union A. W is the critical region and A is the acceptance region. Alternative hypothesis, as I already told, it is called as a research hypothesis. So when I'm saying hypothesis is significant, it means research or alternative hypothesis is accepted. It means your null hypothesis is rejected. Now the reasoning for making the decision, as you can see that there are, it is a two-way table. Null hypothesis is actually true or false, and your decision based on the sample observation, don't reject the null hypothesis or reject the null hypothesis. So we can see that it's a two-way table. There are two correct decisions when you are rejecting the false null hypothesis and you are accepting the true null hypothesis. Moreover, I hope you have noticed that there are two types of errors committed. One is the hypothesis is false, but you are not rejecting the null hypothesis. And another is the hypothesis is actually true. That means the null hypothesis is actually true, and you are rejecting the null hypothesis. So that is called type 1 error. Most of the time we fix type 1 error by the name level of significance, and that's just alpha, and we fix a certain value of alpha, like alpha is equal to 0.01 on 0.05, so on and so forth, and we try to minimize the probability of type 2 error. So this is the mechanism of parametric inference. Okay, and we know if beta is the probability of type 2 error, then 1 minus beta is called the power of a test. So when will we say that a test is a good one? When that test will give you better power. And all of us are familiar with these three types of picture. This is the form of alternative hypothesis when you are testing for left tail test, means less than, and your rejection region will be coming from the left end, and this is for right tail test. Your rejection region will be coming from the right side, and you can see that I have already demarcated the rejection region, that yellow zone, by alpha. And when your alternative hypothesis is two-sided, then your rejection will be coming from both tails, and generally we stick to equal tail test, and you can see that the left tail rejection region is alpha by 2 and the right tail rejection is also alpha by 2. And when we are performing Gaussian or parametric test, as I already told you that parametric test is based on Gaussian structure. So we have to calculate z-score. Z-score is x minus mean divided by standard deviation. SD means standard deviation, and we know that this z-score follows standard normal. Now on the basis of the p-value, what is a p-value? A p-value is the chance of obtaining the observed result. Observed result means your test statistic or extreme, assuming that the null hypothesis is true. Okay, that's the common concept, common definition of p-value. And we know lower the p-value, stronger evidence against the null hypothesis. So as per your p-value, in case you find p-value is less than alpha, you reject the null hypothesis. And if you find your p-value, calculated p-value is greater than alpha, then we fail to reject the null hypothesis or accept the null hypothesis. Well, let us see what happened if the data is not coming in a shape of probability distribution or non-bell shaped. So there is a data which is collected from a study on anxiety performed in a group of 166 normal women, that is who are from outside of pathological clinic in Townsville, Queensland, Australia. So this data is from Australia, and their anxiety level is measured. Okay, it's very interesting data, and the data points are the standard observation, and these points means the anxiety level, and anxiety level generally ranges from 0 to 42, but since we have done the standardization, so here you can see some point values and all. So total 166 data points are here. That's the anxiety data, and let us start a little bit of R for plotting this anxiety data. Let me open the R window. Here I would like to say that I am using RStudio, and I will ask all of you to install RStudio in your laptop or in your desktop whatsoever. And I am using, you can see here, I am using R version 4.4.2 and RStudio that is 2024.12.1. In fact, you can go to the help menu, and in about RStudio, click RStudio, you will see that the version of RStudio which I am using right now for this course. Okay, so what I was trying to say that think about the data. Is it a symmetric data? So how to check it on? You can just go for the drawing of histogram. Here you can see this is the data, and X2 is the grouping or creating group or class for this data. I am trying to group 40 classes, and there you will see that histogram, hist is the drawing of histogram code for R. Now when I am just running this thing, okay, let me run it so that you people will have one clear idea. Okay, so can you see? Well, one point I forgot to tell you that in RStudio you will have 4 quadrant, right? This is this top left quadrant is meant for writing the R script, R program, and this is the environment. This part is for environment specific quadrant, and this place where you will find all of the plots or the packages, this space is allocated for that, and the bottom left corner you will find the console. Console is the most essential quadrant because in console generally the codes which you have written will be run. Okay, now when we are looking at the histogram, it is clear cut that this histogram cannot give you a normal or a Gaussian structure, right? Now if you are more interested, you can go for normal density inlay drawing over that histogram. You see all of the codes I have jotted down here, and also I am going to share this program file with you. So when I am drawing the normal lines, can you see that the red line, that means this is the normal curve. What you can notice out that the peakedness, okay, that the height of this histogram is two-way different from this normal inlay, right? Or else you can check the deviation from normal from the theoretical quantiles. So QQ norm is used for the quantile calculation, and QQ line, it is for normal. So red lines, red dots, which you can see here, red dots are the quantiles calculated from the data, while the blue line, this is the quantile or theoretical quantile for normal graph. As you can see that the red dots are too far from that blue line, that means this data cannot be a normal population, cannot be from a normal population. Now what we can do right for this data? This is the particular case when you have to think about some other alternative or non-parametric test. Okay, so the test statistic in non-parametric is based on the ordered observations. Okay, you have to make the ordering of all the observation of all the sample observation. The computation process is very simple and less stringent to data, especially the outlying observation. So in case you have outliers, nothing to be worried of. Non-parametric methodology will take care of it. Generally, parameter to be tested is taken as median or rank based parameter, and there is one demerit. Already I have mentioned this demerit, that under the fulfillment of required assumption, parameters are always more powerful than the non-parametric test. So what we have to keep in our mind, that in non-parametric we have to fix the parameter to be tested as the rank based parameter. What is rank? We will see it in our next lecture. Now there is a quick glance, the difference between parametric and non-parametric test. So I am leaving this part for the reader, for my students, that okay, what are the assumptions you have to make when you are dealing with parametric test and when you are dealing with non-parametric test. So it is for your home task, you have to go through it. And the references, since this is the first lecture we are traveling with, the references I would ask you to go through: Non-Parametric Statistical Inference by J.D. Gibbons and S. Chakraborty, and a very common book, Fundamentals of Statistics by A.M. Gun, M.K. Gupta and B. Dasgupta. You have to remember that for every parametric test, there exists non-parametric tests. Just to incite your interest, here are a few tests which you are very familiar with while dealing with parametric tests, while dealing with usual tests. And for each of these parametric tests, there exist analogous non-parametric tests. So thank you so very much, and I will ask all of you to practice those R codes so that you can understand that what is the need of non-parametric. Try out with some new data, whether this data is coming from a normal population, whether non-parametric is needed or not needed. Okay, thank you.